mic here is not working. Those of you at the back, can you hear me clearly? You can hear me clearly, right? Those of you at the back. Okay, thank you so much. Now, I want to welcome you to my lecture today. Today, I got two materials. This is going to be the first one. I'm going to walk you through this before we go to the next material. Now, we're starting with reliability today. And I'm going to tell you what is the purpose of this and how can we actually determine the reliability of a system. Let me first I'll start by actually telling you that when we talk about reliability, of course, we mean it should be, a system is reliable if it is trustworthy and if it can actually perform well, perform consistently. Okay, it's actually going to perform consistently, and it's going to do the tasks at a specified time desired for it. But let me tell you this: we live in a world where where there's a lot of variations. There could be success, there could be failure. Okay, and how can we actually assess the reliability of a system? Because we don't want a situation whereby the system will fail suddenly. We don't want that. Okay, so and that is the reason why we need to use the knowledge of probability to determine how reliable a system is. But what do I mean by a system? It's actually, system comprised of components, several components. Okay, either arranged in series or arranged in parallel or the combination of the two. And let me tell you, when components are arranged in series, and you actually want to determine the reliability of the system, you want to determine the reliability of a system whose components are arranged in series. What I'm going to tell you now is that what will determine the success of a system in that situation actually depends on the success of individual components. Because when components are connected in series, they are arranged in series, before the system can work, every component has to work. If one component fails, the system fails. I'm going to say that again. If one component fail, then the system will actually fail. And that is for situation, where components are arranged in series. Okay. Now imagine if I driving on the highway and I don't have a spare tire. Okay, I don't have a spare tire. And of course, my tire get deflated in the middle of highway. That would be disastrous because there's no spare tire. Then the car is going to break down. Okay. But look at a situation whereby I got a spare tire, which means I got a backup. The tire I have in my car is parallel to the one the car is using currently. When I talk about parallel connection, the only condition under which the system is going to fail is if all the components fail. That is for the parallel. If all the components fail, then the system will fail. Now, I want us to look at the series system now and the parallel system. If we want to figure out the probability of reliability based on these two systems, then we're actually going to use two types of events that we have done before. Now, let's start with the series. If I want to find the probability of reliability for series, Of course, I'm actually going to use the idea of independence. If I want to find the probability, if I have 3 components that make up the system arranged in series, if I want to find the probability of reliability, what I'm just going to do is to multiply the probability of respective components. What am I doing? What am I doing? I'm actually applying the what? The independent event rule, which will lead to mathematical rule, which is just going to be multiplying the probability of the respective event. But if I want to talk about parallel connection, of course, in the parallel connection, I'm actually going to use, if I have 2 components, then we're definitely going to use non-mutually. I want you to reason with me now, non-mutually. What do I mean by that? I could remember the other time, the non-mutually is trying to tell you it's either this is working or this is working or both are working. Of course, that will go with the parallel because I told you right now, the only condition under which the system is actually going to fail is if all component fails. Then it means if any of the components is working, if one component is working, okay, oh, thank you. Okay, so if one component is working, then the system is still going to work. Okay, and we have situation whereby we can have the combination of the series and parallel system as well. Okay, so which means we're going to use the combination of the idea. Now I'm going to walk you through. You're going to see the example right now. Take a look at this example right now. This is situations where components are connected in series. Okay, if they are connected in series, take a look at that. A simple computer consists of a processor, a bus, and a memory. Okay, the computer is a system that has more than that component. So right now we are having 3 components, right? The probability that the processor is functioning is 0.99, that the bus is functioning is 0.95, and that the memory is functioning is 0.99. And what I want to find right now, I actually want to figure out the probability that the computer is working. The computer is a system right now that actually has a lot of components. Or what I'm just going to do is to multiply the probability. What I'm actually using, and I'm trying to say the components are independent. That's what I mean. Okay. So that is exactly what we have. And I said, so even though all the components have above 95%, I want you to look at that. Each component, the minimum reliability we have here is the one for bus. But at the end of the day, when we find the reliability of the system, it is less than 95% because we have a 0.89. Okay, so take a look at that. Okay, so this is more example. We can have a situation whereby this is like we have 5 components, and then each of the components have the same probability. All we're just going to do, we can just write 1 and raise it to the numbers of the component. That's what we have. Take a look at that. You know, each component has a 0.97, but the overall system reliability actually decreased to 0.86. Look at that. Okay, so that is it. So it means as you continue to increase the numbers of components in a system, okay, if it is if they are connected in series, then the reliability of the system will be decreasing. Take a look at that. If the numbers of components are actually increase, then the reliability is going to go down. So that's what you can see right there. Okay. I think I provided an IO code. Like I said, you don't need, I'm not going to test knowledge of our, knowledge of the lab, but why am I asking you to do the lab? It's optional because you could get some problems that are complex, and using the software will be so easy. You can decide not to. You are not going to be penalized. Okay, I just created that as an option. Okay, does that make sense? Okay. Now going to the parallel connection now. So take a look at what I have now. Something is connected in parallel. That is the way it's going to look like. And of course, what are we going to do for the parallel connection? It's actually going to be 1 minus the product of the failure. What I have right now is reliability, right? If I want to get the failure for each component, what am I going to do? I'm actually going to subtract each of them from 1. Then I'm going to multiply them. Then I'm going to subtract the result that I have from 1. Okay. And that is exactly, take a look at that. I told you when you're talking about parallel connection, if at least one component is working, the whole system will be working. I think you know that for parallel connection. And that is the reason why I said the probability of at least one component functioning will be equal to 1 minus the probability that all components fail. Why do I get that? The probability of S greater than or equal to 1 is equal to 1 minus the probability of X less than 1. I think you know that, right? So that is exactly, so you're going to find the failure of each component, you multiply them, then you subtract. And for you to find the failure of each component, or what you're going to do is to find the complement of the reliability. Yeah. Oh, okay. So I'm using this, right? Do you know the 0.03 here is failure. The reliability given is 0.97. So you're going to find the complement of that reliability, which is your probability of failure. Then you're going to multiply them. When you multiply them, then whatever you get, you're going to subtract from 1. Why are you doing that? You are doing that because in a parallel connection, at least one component needs to be working for the whole system to be working. So and that is why, so the probability of at least 1 is the same as 1 minus no component is working. So no component fail. That is why you subtracted a 0.997 from 1. Does that make sense? Okay. Okay, so you can go through that. I provided an R code. This is going to be so easy. For instance, take a look at this. You got 10 components, okay, and each of them has a 0.97, okay, and as reliability, and they ask you to figure out the reliability of the system. When you write a code, okay, K, 1 to 10, each with the probability of 0.97. You can even make a graph of that. What if I ask you to do that in exam? If you go and use a manual way, I'm still going to grade it, but that may waste your time. Okay, so take a look at that. And that is what I plotted over there. Take a look at that. Now, we can also have the combination of a series and parallel connection. Okay, we can have the combination, and let me show you. Take a look at that. Okay, it's 0.95. 0.95 is in series, but look at 0.7 is 0.7. That is in parallel. Take a look at that. You have the combination of both series and the parallel connection. So take a look at that. Now, what am I going to do? The one in series, I'm going to multiply their reliability. That C1 and C2, they are in series. I'm going to multiply their reliability. But if you take a look at C3, it's a parallel connection. What I actually need to do, I need to first find the failure of each component. And after that, I'm going to multiply them. Then I'm going to subtract from 1. And that's exactly what I'm doing. Give me 1 second. That's exactly what I'm doing here. Take a look at that. Okay, you're going to do the same thing to that one in parallel. Then you're going to multiply by the one in series. So whatever you get is actually going to be the reliability. Oh my God, if you want to do that in now, look at this. Look at the effort there, but look at in now, very short code. Okay, go ahead. No, if you have series and parallel, you're actually going to take, oh, this is it. Let me show you something. C1 and C2, they are in series, right? I need to first resolve the components to be 1 so that C3 is going to be in series with C1 and C2. Because at the end, I'm still going to take all of them to be in series so that I can multiply them. But I need to 404 resolve for the component, okay? So you can see at the end of the day, you are right. At the end of the day, they're all going to be independent in the end. Does that make sense? Yeah. Okay. I put a lot of example that you can actually go through. Okay, it's so easy. Okay, so take a look at that one. So I put a lot of example. You can actually go through them. Okay, I provided an R code and so on like that. You know, for that. No, okay. So I'm gonna go to the second lecture of the day. Give me 1 second. Okay. Let me make it so. Okay, so. Okay, so I want to welcome you to the second lecture of the day. We are officially we are starting chapter 3 today. This is a random variable. Okay, before I move on, those of you online, can you guys confirm if you are hearing me clearly?
I can hear you.
Okay, thank you so much. Thank you for confirming that. I want to welcome everyone to this chapter, random variable. Of course, what are we going to do here? We find ourselves in a stochastic world. When you look at random variable, if I break that, I'm going to, we got 2 words, right? Variable, random. We need to first understand what is the meaning of variable and what makes a variable to be random. Okay. Now in the outline, we're going to focus on 2 different kind of random variable. We're going to focus on the discrete random variable. We're also going to focus on the continuous random variable. But let me first start. What is variable? You know, a variable is anything that is liable to change. Anything at all that's liable to change. That's what we call variable. Like I said, we live in a world where that is full of variation. I want to tell you the way. If you want to look at the way I teach, I want to believe, depending on the mood, depending on certain factors, the way I teach in a particular day may be different, may not be exactly the same as the way I teach in another day. If somebody go to hospital and they take the blood pressure, maybe around 9 a.m. in the morning, if they should go back and take the blood pressure again, probably around 11, they're actually going to record a different value. Okay, I want to believe, I ask myself, what is responsible for that? The conclusion is there is a natural variation that is inherent on any activity. That is my conclusion. Okay, now when we talk about random variable, this is the situation. Anything we do in life, we are in a life of experimentation. It doesn't matter, you don't need to be in a physics lab, you don't need to be in a chemistry lab, you don't need to be in a biology lab before you can experiment. Okay, life is an experiment. Anything that generates an outcome, whatever we do, we're actually going to generate an outcome. But you know what? With no possibility. The possibility is a sample space. I'm going into a business. He said that I know before going to that business, I know the possibility. He said that I record profit or loss. But you know what? The random variable is a way of assigning figures to the element in the sample space. I'm going to say that again. A mapping function that assign numerical values to the element in the sample space is what we call random variable. Now, when the random variable is discrete, it means it can be expressed as a whole number. Example, the numbers of goals in a football match, or the numbers of points in a football match, numbers of goals in a soccer game, the numbers of students that I have in this class right now, those are discrete random variable. If I want to talk about continuous random variable, on the other hand, I'm trying to refer to a set of values that cannot be expressed as a whole number. Okay, it can only be in an interval. Now I'm going to demonstrate to you now. Take a look at what I have here. We got different values of, you performing the same thing and you are recording different kind of values. Okay, so, and that was why I said a numerical value to each outcome of a particular experiment. You have an experiment and there's a particular value because whatever we do in life is quantified. I want to tell you that anything we do in life has a number, can be quantified. Okay, so a way of assigning figures to events or to outcome is what we mean by random variable. Now, I want to give you an example right now. I'm talking about machine breakdown. If a machine break down, I want to believe there is nothing that happen without, when you have a cause, there's going to be an effect. Cause, effect. Okay, what causes the breakdown? Now we know the possibility of what caused the breakdown. It could be due to electrical, it could be due to mechanical, it could be due to misuse. If I have a car and it's breakdown, and the possibility of sample space, okay, maybe due to electrical, due to mechanical, or due to misuse, those are sample space. The way they are right now, there is no figures. If you now want to assign figures to them, then you actually need to have a purpose. For instance, a machine breakdown, of course, you need to repair it, right? Then the random variable here is actually going to be the cost of repair. Now, based on your experience, if a machine break down due to electrical issue, you actually spend $50 on average. When it break down due to mechanical, you spend 200. Oh my God, when it break down due to misuse, you spend a lot, $350. Now, if you take a look at the state space now, what you have in the state space, each of them, that's a random variable. You have assigned figures to the element in the sample space. The initial element in the sample space, they were electrical, mechanical, and misuse. But right now, your random variable is actually the cost of repair of each of the elements in the sample space. Does that make sense? So here you have already identified your cost. Now, let me tell you this. When you identify your cost, every event has its corresponding probability. I'm going to say that again. Every event has its corresponding probability. And you know what? When we are talking about discrete random variable, if we had all the probability associated with every event that we have in a sample space together, it should give us 1. That's what it means. Summation of the probability must be equal to 1. And of course, the probability of whatever event must lie between 0 and 1. Okay. Now, then I can actually find what is the probability if X is actually a random variable or based on the the machine breakdown. It could be 50, it could be 200, it could be 350. But what if in a situation where the interest probably maybe I actually want to figure out what is the probability that when my machine break down, what is the probability that I'm actually going to spend $90? A question like that can actually be answered. Okay, now if you want to take a look, there's something that we call probability distribution. What do we actually mean by probability distribution? The probability distribution, we derive that from something that we call frequency distribution. When you talk about frequency distribution, even we have different events, right? Some events occur more than others, right? That's what, So, of course, if some events occur more than others, there's some event we have more probability than others. Now, when you take a look at what I have, what is the meaning? You know, the 0.3 means 30% of the time, if my car break down due to electrical issue, I spend $50 for repair. 30% of the time, not all the time, 30% of the time. You actually derive that probably based on your experience. Okay. Then 20% of the time, if my car break down and it is due to mechanical, I spend $200. That is 0.2. 50% of the time, if it is due to misuse, of course, what I spend is $350. Okay. Now, when you look at what you have in the box, that is what we call probability distribution. It is called probability distribution because you have the possible, you can say the possible numbers of values a random variable can take with their corresponding probability. Now, if you now want to know the trend, if you now want to look at the shape of the distribution, then you can have a plot. Okay, so when you plot, the probability against the random variable, this is what you are getting right now. Okay, so this is a probability mass function plot. And you know what? If you take a look at what I have, it means the probability that the cost is going to be equal to 50 is 0.3. That is what I have there. I'm just trying to interpret what I have in the box. Okay. Now, the next thing that we're actually going to do is we actually want to obtain what I call the cumulative distribution function as well. What do we mean by cumulative distribution function? At times, if you want to figure out a probability question that asks about what is the probability that I'm actually going to spend less or equal to 70, less or equal to. A question like that can be answered just, by using the cumulative distribution function. So we can use a cumulative distribution function to answer a lot of questions. It can be used to answer a question of, what is the probability of X less or equal to a realized value? In fact, we can also use to answer a question of what is the probability that X is going to be greater. For X to be greater, there's going to be 1 minus the probability of X is less or equal to. And you can also use that to answer a question that has to do with what is the probability that, a random variable lies between A and B, stuff like that. Okay. Now, this is the plot. Before, what I have right here are the cumulative, okay, that I plotted against the random variable, and it is expected it's actually going to look like a staircase. Take a look at that, okay, terminating at 1. Okay, take a look at that. Okay, so what I'm going to show you here is just how to compute the CDF. I want us to see, if you look at the first one, minus infinity less than 50, less than X, less than 50, of course, the probability of that does not exist because based on the question we're solving, the minimum cost is $50. What I have there means less than 50. That is why the probability is 0. Okay, so take a look at that. I'm trying to accumulate, and you know what? The CDF must cumulate to 1. Okay, that's what I have right now. Okay, so I've been talking about discrete random variable. Well, of course, we're still going to answer a lot of questions on the discrete, but for now, I quickly want to go into continuous. Okay, random variable. I told you the other time. As for continuous random variable, the variable cannot. It's a continuous random variable is a variable that arises by measurements. Okay, but for discrete, the variable that arrive by counting, when you count, but this one by measurement. Okay, I want to give you an example right now on meter cylinder production. Suppose that the random variable X is the diameter of a randomly chosen cylinder manufactured by the company. And since this random variable can take any value between 49.5 and 50.5, then we're going to refer to that as a continuous random variable. Okay. Now, let's study about the property of a continuous. The other time, under the discrete, We call the name of the probability distribution for discrete probability mass function. But for continuous, we call it probability density function. Because in the continuous, we're looking at the area, the total area under a curve. Now, what we're trying to say, f of s greater or equal to 0 means, the probability has to be greater or equal to 0. I think you know that. And under discrete, we said the sum of probability must be equal to 1, right? But under continuous, we don't talk about sum. We talk about antiderivative. Take a look at the integral. The integral f of s ds equal to 1. You remember last time I told you, for you to be able to understand chapter 3, you need to revise your knowledge of basic calculus. Okay, so you're going to make sure you revise your knowledge of basic calculus. Now, this is a takeaway. Before I can use a function to find the probability of any event, before I can use a function to find the mean, before I can use a function to find the variance, that particular function must be a valid probability function. What do I mean by valid probability function? If it is a continuous one, it must integrate to 1. If it is a discrete one, the sum of the probability must be equal to 1. That's what I mean by valid. It has to be valid. Okay. Now I want you to take a look at this right now. I'll give you 1 second. Okay, now let's have this example. We're still talking about the diameter, and of course, according to the company, the diameter, lies between 49.5 and 50.5. And you know what? Based on the experience of people in this company, they develop a mathematical function that relates a probability with the values of a diameter. They got 1.5 minus 6 into x minus 50.2 all squared. Of course, x actually represents, the values of the diameter. Now, f of s equal to 0 means, otherwise, elsewhere means, if we're talking about a range other than that, then the f of s does not exist. The only condition under which f of s exists is if and only if, the neighborhood of x should be between 49.5 and 50.5. When you make an attempt to plot f of x, okay, against the values, this is going to be the shape. Take a look at that. And if you take a look at this shape right now, the total area under that must be equal to 1. Do you know that probably in assignment 3, I can ask you a question, like I give you a function, and I ask you to check whether it's a valid PDF, just like this. Take a look at this. It's going to be a valid PDF if I actually work on the antiderivative, and the result that I got is going to be 1. If it is 1, then it's a valid PDF. So I'm using this opportunity to tell you to actually revise your knowledge of basic calculus. I said basic. You don't need a complex one, okay? Just basic one, okay? Okay. What if in a situation where I'm not interested in the entire range? I'm only interested in the words in the shaded parts. Of course, you expect the probability that I'm actually going to get to be less than 1, right? Because the total area under a curve is equal to 1. If I want to do that, I'm still going to perform the antiderivative, but only that the bound that I'm actually going to use will be different, okay? Now, between 49.8 and 50.1, I got the 0.432. Oh my God, what does that mean? 0.432 means 43.2% of the time when the measured diameter is between 49.8 and 50.1. That's what it means. You make sense of your probability value when you multiply by 100. Okay, go ahead. Or whether you can use a graphic calculator for the exam, it is not allowed. But if you are doing assignment, you can use whatever. You get what I mean? So the instruction for the exam will soon be released. Don't, like, this is what I always do before exam. I normally dedicate a class for reviewing practice questions, telling you the expectation, telling you what to bring in, what not to bring in, and stuff like that. Does that make sense? So I'm still going to talk about that one. Okay. The next thing that we want to do now is cumulative distribution function. Of course, I walk you through the cumulative distribution function for discrete. We want to do the same for continuous, but only that the way we actually compute the cumulative distribution function for continuous is different from the way we did that for discrete. Now, I want you to pay attention to the board right now. When I'm talking about PDF, probability density function, that's a lowercase f. If I'm talking about CDF, cumulative distribution function, that's an uppercase F. Okay, uppercase F. Now, if I want to get a CDF, which is an uppercase F, for a continuous random variable, and the CDF actually means what is the probability that a random variable will be less or equal to a realized value. Look at that. The probability of a random variable less or equal to a realized value. What am I going to do? I'm actually going to start the range. It's actually, I'm going to start from the lowest point to that particular point. Okay. The general formula is going to be start from negative infinity to x. But in the case of the question that we're doing here, in the case of this one, I'm actually going to start from the lower point, 49.5 to x. Does that make sense? So I'm going to show you how that can be done. Okay, so if I can actually obtain the CDF from the PDF. If I want to get a CDF from the PDF, or what I'm just going to do is to integrate using the range of the lower point to that particular point. Okay, so if I'm working on x, then I'm going to write f of y dy or f of t dt or something like that. And if I want to get my PDF from my CDF, then I'm going to differentiate the CDF. Of course, derivative, antiderivative. Antiderivative is the inverse of that. So what I'm trying to talk about now, the CDF, also the inverse, when you integrate the PDF, you get a CDF. When you differentiate the CDF, you get a PDF. That's what I'm talking about there. And you can use the CD, if you get the CDF of, at a particular point S, you can use it to answer a question that has to do with what is the probability that a random variable X will lie between A and B. Or what you just need to do, the CDF that you've derived, plug in B to represent S, plug in A. What is B and A? B is the upper bound, A is the lower bound, then you're going to subtract. Okay, so that is what we're trying. And you know what? When we are talking about continuous random variable, there is no difference between less than and less or equal to. If you are talking about continuous random variable, there is no difference between greater than or equal to. If you are talking about continuous random variable, there is no difference between this and this. In fact, there is no difference between this and, any form of this that could, where A lies between, where S lies between A and B. Now, the PDF we're working on, how can we find a CDF given a PDF? I'm still using that diameter of function right now. What are you going to do? You're going to write a function, the PDF. You're going to start from the lower point. The lower bound given was 49.5. Then you're going to terminate at x. When you terminate at x, you don't write. You can say that I'm changing every other thing to y. You can change it to y. You can change it to t or whatever, but it has to be other than x. Then you're going to integrate that. You're going to do antiderivative. Then you're going to plug in x. Then later you're going to plug in 49.5. Then you're going to subtract. Now, when you take a look at the result that we have for the CDF now, which is an uppercase f of x, is going to be 1.5x minus 2, which is this guy here, minus 2 into x minus 50.5 or 0 raised to the power 3 minus 74.5, that is a CDF. Okay, the big F of S, an uppercase F of S. Now, I can use that CDF to answer any probability question. For instance, I want to use it to answer the probability of X, the random variable lie between 49.7 and 50.0. Or what I'm just going to do, oh my God, plug in 50, wherever you find X, compute that, plug in 49.7, wherever you find X, compute that, then you subtract, then you get your result. It's easy as that. Now, lastly, for today, how do we plot the CDF of a continuous random variable? Now, I'm going to go back. You're going to go back to the CDF that we derive. Okay, that we derive using values of X. If you plug in some values of X into that, but the values of X, you're actually going to plug in, you're going to make sure it lies between 49.5 and the highest. Okay, going to make sure at the end of the day, when you plot that, this is what you're going to get. This is what you're going to see. Okay, this is what we're going to see. You know what we just find now, you know, the other time if you want to find between 49.7 and 50.0, this is for 49.7 and that is for the 50.0. And of course, we're looking at the distance. Okay, so we'll take a look at that. Okay, so the distance between that and that is you're looking at the probability of X lie between that and that. Okay, well, what are you going to read for this? You're going to read chapter 3 and some problems in chapter 3. And I want to confirm to you, this time around, some questions will come from the textbook for the assignment 3. Okay, so because of that, whatever we're doing now that relates, what you have in chapter 3 that relate to what we're doing now. So I would advise that you start reading them. Tonight, I'm actually going to make a suggestions for some exercise. Okay, so you watch out for that. Okay, lastly, because I see I have time, I quickly want to talk about practical assignments. The practical assignment part 1, I've already released instruction. Do you know all what I need in the practical assignment part 1 is just for you to decide on the topic you want to work on. Let me tell you, you can decide to work alone, and you can decide to work with group. But if you want to work with group, the maximum number of people that I can tolerate in a group should be 3, maximum. Okay, it means you could be 2 in a group. Okay, go ahead. Oh, okay, so if you decide to work with people in another section, right? That is if it is section that I'm in charge. You know, I'm in charge of this section. I'm also in charge of another section. So if it is that, then there's no problem. Okay, so there's no problem at all. Okay, so like I said, you're going to decide on the topic you're going to work on. You're going to share what you want to work on into I'm going to create a practical plot on Canvas. You're going to turn in what you want to work on. Think about what you feel like we could work on. Probability, you could work on. There's still a lot of topics we haven't done. Maybe what I'm going to do is this. I'm going to upload, the project format, which should be the project written by my student in the past. I'm going to upload that. That will give you a guide on how to go about it. Does that make sense? Okay. Yep. Right. Oh, before you. Yep. Oh, you mean whether they're going to be countable, right? Did they say countable? Yeah. Actually, what we're talking about here, we're talking. You understand what I mean? Like continuous random variable, right? They cannot be expressed as whole number. Now, let me give you the example. Yeah, so exactly. Oh, the area, this is a different graph. Oh, okay, okay. Do you want me to go to the one you're talking about? Okay, give me 1 second. Like this one now. Exactly. Exactly. So if it is discrete, you are right. If it is discrete, you're going to add all the probability, there will be 1. If it is continuous, you're looking at the total area under a curve. From here to here, that will be 1. And right now, if you're focusing on this alone, you're going to get less than 1, right? That was why you have a 0.432. Does that make sense? Yeah. Okay. Oh, okay. Go ahead. Oh, which one you call the one? If it does not integrate to 1, like what I'm doing here, that's a very good question. You know, I can give you a function in exam, and I said investigate whether it's integrate to 1. If it's integrate to 1, it means it's a valid PDA. And what is the meaning of that? What is the implication of that? If it's a valid PDF, you can use it to answer a probability question. If it's a valid PDF, you can compute the mean, you can compute the variance, but if it is not, we cannot do all those things. Does that make sense? Yeah. Okay, make sure you stay safe and have a good day. This of you online, do you have any question you want to ask? Um, do you have any question you want to ask versus you online?
I'm okay, thank you.
Oh, you're welcome.
Thank you for class too. Thank
Oh,
you.
oh,
Have a
thank you
nice day.
too. Okay, thank you too. Okay. Yeah, how are you? Oh, okay. So I'm gonna explain why you have that 6% and 10%. This is what I'm gonna do. Do you have the solution? Has he uploaded the solution? Okay, yeah, I actually confirmed that it's correct. But so you know what I'm gonna do? Um, I'm gonna check my time, or probably during the office hour. Then I'm gonna explain everything to you, how how that is the result. Does that make sense? Yeah, I'm gonna explain to you. Okay. Yeah, you're welcome. So I'm gonna be having my office hour. I think my office hour is every Tuesday and Thursday. Tuesday 10 to 12 office hour. No, you can just join the Zoom. You join the Zoom Tuesday 10 to 12, or you join the Zoom on Thursday from 12. Yeah, I think I just updated my syllabus. Some people, I have some students that visited my office hour yesterday. So then I'm going to explain. Oh, you don't know how to find where to find what? Oh, TS email. No, TS email is on the canvas. Yeah, on the syllabus. I put his name, everything. Yep. Yeah, you're welcome. Yeah, how are you today? I'm good. Yeah. Because the two sessions are under me. Yeah, that's a problem. You're welcome.
Continuous part of like, so when does that come into play? Like, if it's like, what criteria makes something continuous? Is it saying like there's like if you give like a range of like 1 to like, if you say 1 to 5, you can have infinitely as many like numbers.
Exactly.
Whatever one, and that's like its own, and you can just keep on. So that's when it's continuous.
Yeah. I think you just answered the question. If you have, let's say, 1 and 2, discrete, only two numbers, 1 and 2. But if I want to treat 1 and 2 as continuous, there's a lot of numbers in between.
So with discrete, that's the more simple way, like very simple stuff.
Exactly.
This is for continuous.
Exactly.
Okay. So they're including with this one, they're including possibility of 49.5, 49 point.
But you know what? Do you know that 49.5 is not part of, you're saying X lie between, it could be part of that, it may not be part of that. But what happened is that there's a lot of values in there, and that is the reason why if they say what is the probability that a continuous random variable will be equal to 5, can you tell me that? What will be the probability? You have a continuous random variable now. What probability is going to be equal to 5, or it's going to be equal to an exact number?
An exact number, it's going to be very rare.
Very, it's going to be 0 because there are so many. Yep.
So whenever you have a range, that's why like you kind of like, with like when they give you a function, you get the antiderivative of it, and then you get the area of the ranges between. That's why it gives them.
Yeah. Yeah.
All right. Well, that's gonna take some time.
Okay. How are you today?
Doing all right.
Okay.
For information on the practical assignment, I noticed that there's the guide online. Is there a set of dates when all the parts are due?
Yeah, I think I put that in the syllabus for practical 1, for practical 2, for practical 3. And tonight I'm gonna put that on Canva I'm gonna just like the way I used to curate weekly assignments. So there's gonna be a part for practical 1.
Okay.
Yeah.
Thank you.
You're welcome. Yeah, how are you today?
Good. How are you?
I'm good.
Okay, so I'm just confused about the difference between a PDF and a CDF. So you explained PDF, whereas like you're trying to find the probability of it being a certain, like out of all the possibilities of one, you have a certain percentage of like being in between this number and this number, right? So what is a CDF then?
Oh, what is CDF then? Yeah.
What I described as PDF, right?
Yeah, the CDF, you're like, what is the probability that I'm going to spend less or equal to 20? That is a CDF. Less or equal to 20, like you're coming from a lower point to a particular point. You're coming, all the way from the lower point to a particular point. That's a CDF. Okay, so the CDF answer a question of, what is the probability of something less or equal to? And it's very useful in survival analysis. I'm going to tell you why. A patient that they are managing in hospital, what is the probability that is going to die within 3 years of intervention, or within 3 months of intervention? That will be probability of X less or equal to 3. But when you want to talk about survivor now, what is probability that you're going to survive beyond that you're talking about? Greater than, right? If you want to get greater than, then you need a CDF. So 1 minus the CDF will be the survivor, will be the greater than. Does that make sense now, right?
But then when do you use like whenever you see a function, you do the integral first?
Oh, no. I think I get what you mean. It depends on what it asks you to do. For instance, we are given a function. Probably the instruction may be, or show that it integrates to 1. Of course, you're going to integrate that and use the range provided. Or the question say, what is the probability of X